Hello students, welcome to the second part of the switch capacitor circuit. So we will be discussing about the hold phase, which is a phase in which the switch basically is off and the output capacitor CH holds the sample data. But this non-idealities in general causes some errors into the value that is read onto the output capacitor CH. And one can categorize these errors into three types. The first one, the droop. The second is known as clock feed through. The third one, the channel charge injection. So now we will discuss about the origins of these errors along with the possible way to rectify these errors. Droop is basically a phenomena where the charge that is stored on the capacitor CH leaks due to the non-ideality of the capacitor CH. So one can model this leaky capacitor as a kind of ideal capacitor in parallel with a resistance which mimics the parasitic resistance of the device. Let us assume that this leakage occurs linearly over a time before the switch is again turned on, and one can plot the linear degradation as something like from its initial value, which would be equal to Vin, because that would be the last value that was sampled before the hold phase, and this Vin value would get degraded over time linearly. This change in the value of Vin is represented as del V, and this del V represents the error introduced due to the leakage, and the derivative of this dV out with respect to dt represents the droop rate. Now, most of the time the design has to have some specific tolerance value on this degradation of this value. We know that the output gets degraded from the initial value as the time progresses. So if the design specification demands this delta V to not to change more than 1% of the initial value, which in general would be Vin, then it constrains the maximum time that the hold phase would be on, and in turn it also defines the minimum frequency of the switched capacitor circuit. Next, we discuss about the second type of error, which we call it as a clock feed through or charge feed through. Now this phenomena basically happens due to the overlap capacitance between the gate that is shown in the blue to the drain, or between the overlap between the gate and the source terminal. Okay, so there is basically a particular portion that overlaps. So this overlap in general creates a capacitance, and this capacitance in general is always expressed in terms of farad per meter, where this meter represents basically the length of the overlap, and this value would be constant for the technology that we are working in. Okay, say for 180, there will be a specific value of this overlap capacitance for NMOS, as well as there will be a specific value of this overlap capacitance for a PMOS. Okay, so now when you take as a transistor, the transistor in general will have a specific width, right? And in order to evaluate the total overlap capacitance, what we have to do is this capacitance, which is the capacitance that I've shown here, and which I said it is representing a constant value for a technology that we are using, in general is denoted with the letter COV, where it has the unit of farad per meter. And now in order to calculate the total overlap capacitance, then one has to multiply with the width of the transistor. So I have a unit for the first term as farad per meter, and the second one has a unit of meter, so that the meter get cancelled, and effectively I would get a unit for the total capacitance or the total overlap capacitance to have a unit of farad. Now the same could be modeled schematically as shown here. Now each of these capacitance denotes the overlap between the gate and the drain, and the gate and the source, and the total overlap capacitance is generally written as COV times the width of my transistor. Now during this phase transition, where from the sampling to the hold phase, the clock generally makes a negative transition, and this transition has a magnitude of delta VCK, and in general it will have a negative value just because it makes a negative transition. We also know that the capacitance conducts only when there is a change in the input signal. So we can visualize these capacitors to have a certain specific impedance across them. Now I try to mimic those impedance value along with the change that is happening at the output node. So the CH would define an impedance value of 1 by SCH, and the overlap or the total overlap capacitance would have a specific impedance value which is defined as total overlap capacitance. And now when there is a change whose magnitude is equal to delta VCK, then it induces a change in the output voltage, which let us denote with a value of delta Vout. Okay, so now we just want to evaluate how much is the change that is happening across this delta Vout. So in order to evaluate that, one can use the voltage division rule, which states that the delta Vout is defined as the impedance posed by the hold capacitor, which is 1 by SCH divided by the sum of these two impedances. Yeah, so now after eliminating all these common terms, one would end up having, so this is the change that, so the delta VCK in general will have a negative value, okay, and due to which ideally during the hold phase our Vout should have the value of Vin that we had just before the hold phase, but this value right now, due to this clock feed through impact, would get reduced by this delta Vout, and the magnitude of this delta Vout is expressed here. Okay, so certainly the value that we wanted to hold is Vin, but it has got reduced by this delta Vout just because of the overlap capacitance. Now one has to note certain things in this delta Vout expression. This delta Vout expression clearly states that this particular delta Vout doesn't depend on Vin term, and that is one of the advantage. So what I really mean as an advantage here is that magnitude of this delta Vout is always a constant irrespective of whatever the Vin that I have sampled during the sampling phase. Okay, so if this particular error is a constant, then one can easily eliminate this error. Now we will focus on the last type of error, which is termed as channel charge injection. This error also appears due to the transition from the sample phase to the hold phase. To understand this channel charge injection error, first let us try to evaluate the channel charge that I would have under this particular gate when the clock is high. Okay, so what would be that value? We know Q in general is basically equal to CV, right? So we can use this expression to calculate the total charge that I have stored under this channel when the clock is high or when the NMOS transistor is on. So which is nothing but I would represent that channel charge to be equal to QCH, and that could be expressed as the capacitance, and I know that the value of this capacitor COX is defined as farad per meter square. Okay, and so in order to evaluate the whole transistor's capacitance value, I need to multiply its width and its length. Okay, so this represents the total C that I have represented here, and now that we have to represent the effective gate potential, so which is nothing but VGS minus VT. Now out of this VGS, we can represent the VGS as VG minus VS, where VG when it is on is actually connected to my VDD, so I can replace this VG with VDD, and what is available across this source is nothing but our Vin that is getting translated across the source terminal, right? So I can replace this Vs with the value of Vin, and this is the effective value of VGS. And now the moment the channel is turned off, okay, by making a negative transition, what happens is these channel charges has to dissipate from this channel. Okay, so it has to flow out from this particular channel. So what it generally does is, like, the channel charges will try to move towards the drain as well as towards the source. Now the amount of charge that flows towards the drain or towards the source depends on the impedance that is seen across the source terminal and across the drain terminal. Okay, so here the impedance that I am saying is not the small signal impedance that I am talking here. Okay, so please make a note of it. Okay, yeah. So now let us assume that the impedance that the charges that sees here from the channel happens to be equal for both the drain and the source. So what happens is, then half the channel charge would try to dissipate by moving towards the drain. The remaining half of the channel charge would tries to go towards the source in order to discharge to the ground, right? So in this particular movement, the movement of these charges in general flows across the capacitor CH top plate and tries to disturb the charge that I have stored before the hold phase, which means that the Vin, which is stored as a charge here, would get disturbed by the charge that is coming out of the channel. Okay, so due to which the Vout actually gets disturbed. So nominally the Vout in general will be holding a value of Vin during the hold phase. And how do I evaluate the voltage that this particular charge would induce onto this capacitance? We again could make use of the same formula that we have discussed before, which is charge Q is basically defined as a multiple of capacitance times that of the voltage. So now I know what is the charges, and I know onto which capacitor these charges are moving on. The only thing is I need to know Q CH by 2 is the charge that is flowing towards the capacitor CH divided by the value of CH. Okay, so this is the change in the potential that happens to occur on our Vout, or the output voltage Vout gets disturbed by this amount of voltage. Now let us try to re-represent this channel charge with appropriate expressions. Okay, so I'm just trying to expand this QCH with so now I'm just going to take out this Vin term in common from this term. So I would get something like 1 plus the oxide capacitance multiplied by the width and the length divided by twice the hold capacitance times that of Vin minus the oxide capacitance, the width and the length times that of VDD minus VDH divided by twice the value of the output hold capacitance. Now clearly from this expression there are two types of errors. Okay, so the first error is basically named as gain error, for the reason just because it disturbs the ideal value of output voltage supposed to be our Vin, but rather than this Vin we also have some extra term that is getting added. So that's the reason why it is termed as a gain error. And the second term represents a constant DC offset error. Okay, so basically this is a constant offset error. Okay, the reason here is the terms that are involved in defining this second term basically are constant in nature. So either it could be VDD or it could be our VT, right? So that's the reason why we have this DC offset error. And in general the DC offset error, which is basically constant, could be eliminated suitably. But these terms are actually evaluated on the assumptions that there is no body effect. But we know that the body of an NMOS is generally connected to the ground, whereas the source is not connected to the ground, right? So there is always a potential difference between the source terminal and the body, and due to which one has to encounter even the body effect. So we know the body effect impact could be modeled by change in the value of the threshold voltage of a device, right? So what would be the new value of a threshold voltage when there is a body effect? this is nothing but it could be defined as Vt naught, where Vt naught is the threshold voltage when there is no body effect, plus gamma times that of square root of 2 phi f plus Vsb minus square root of 2 phi f, right? Yeah. So now when we look clearly into the potential of Vsb, one can rewrite this Vsb as Vs minus Vb. And as I said before, the body of an NMOS is generally connected to the ground, so this term goes to 0. But what is connected to my Vs during the transition from sampling phase to the hold phase? It would be equal to Vn. Okay, so effectively the Vsb term is related to the value of Vn here. So due to which the new value of threshold voltage is defined as Vt naught plus gamma times that of square root of 2 phi f plus Vn minus square root of 2 phi f. And now that I want to plug in this new value of Vt into the DC offset error, okay, so this term has to be replaced with this new term. So again, when I try to plug in, what happens is the gain error term would stay as it is. It's only the DC offset error right now has to be re-returned, and I will take only this second part of this expression and trying to rewrite this second part to be equal to twice Ch and VDD, and generally this Vt naught would be a constant value, so I just take it here, and even this square root of 2 phi f will also be constant, so I'm also adding it here with gamma times that of 2 phi f. Okay, and the remaining term is basically this particular term, so which I will be putting it outside. So clearly we could able to see that this particular third expression has a term that involves the value of Vn, and in general this Vn induces a nonlinear error. Now why does it induces a nonlinear error? So to answer this question, we have to look back to our Taylor series. So I'll just use this particular slide. Okay, so we know that one could represent this square root of 1 plus x, which could be written in terms of Taylor series as 1 plus ax by 2 minus x squared by 8 plus x cubed by 16, and then there is a negative sign, so there will be an alternate negative sign and positive sign when one goes on for higher order x terms, right? So this is what happens here. So you could be able to clearly see that the value of Vn is basically being squared and then cubed and then powered with different higher order terms. Okay, so these quantities in general introduces a nonlinear relation between the Vout and the Vin value that we have. Okay, and that's the reason why this term causes a nonlinear error into our expression. And obviously the second term is involving all the DC quantities, so this could be again re-returned as DC offset error. So we generally end up having one gain error, a DC offset error, and then a nonlinear error. So pretty much seems to be a very difficult type of error that we have right now, just because of the nonlinearity error. Okay, so generally this becomes quite difficult for us to eliminate all these three type of errors that are being categorized under this channel charge injection. Okay, so now let us look at the methods in order to remove this channel charge injection problem along with what is termed as a clock feed through errors. Now let us look at the methods to eliminate the channel charge injection as well as the clock feed through error. Okay, so these are the proposed way by which we try to eliminate both these type of errors. As a first method, we'll look into our dummy switch. This dummy switch basically relies on the idea that we know that these channel charges, when we try to turn off the device, will try to tend to move towards a part of the channel charge would try to move towards the output and tries to disturb the charges that is stored on this capacitor. Okay, so now what I'm going to do is, like, by making use of a dummy switch, I want to utilize these charges to create the channel that is required by the dummy switch. Okay, so this is again has to be operated with a different signal. Okay, so say for example, if this is my phi 1, then I need to operate this second transistor, which is M2, by phi 1 bar. Okay, so basically a non-overlapping clock signals. So what happens is the moment I make a transition, or the moment I turn off the device from on to off, then this device has to be turned on by applying a gate potential which switches from 0 to VDD. So the moment it reaches VDD, then it requires the channel to be created over here. And what I'm going to do is I'm going to grab these charges in order to build these charges. Okay, so let us try to first assume certain charges that are moving here. So let me assume that the channel charge that is moving towards the source or towards this Vout is assumed to be half the value of the channel charge that I had under this M1 transistor. And now the moment this is turning off, I'm going to turn on the M2 transistor. Now this also requires some channel charge, which I take it as delta Q2, and let me represent this amount of charge to be equal to delta Q1. Okay, so now what is the channel charge that I can represent when it is turned on? It's nothing but the same formula that we use in order to evaluate the channel charge when this particular transistor is on, right? So which is nothing but the oxide capacitance times the of the width into the length of the M2 transistor, which is totally representing the C value, and then the effective gate potential, which is equal to VGS, where VG is connected to my VDD, and this node is actually trying to hold the lastly sampled value of my Vin, right? So generally the source is also again connected to my Vin that I have stored here, so I can still retain the same value of Vin for the VS term, and then the threshold voltage of the second device. Okay, now in order to capture all of these charges to completely create the channel charge under this M2, I need to make sure this delta Q1 to be equal to delta Q2. So what I really mean by that is that I need to re-express this QCH, right? So what is the value of QCH? So QCH is again defined as the oxide capacitance times that of the width and the length of the M1, and then the effective gate potential, which is VDD minus that of Vin minus VT1. Okay, and this, the assumption of only half the channel charge moving towards the output is taken care here. So that's the reason why the factor 2 comes at the bottom, and that has to be equated to this whole chunk of expression towards the right. So now clearly, if both these quantities are equal to each other, then our job is done. Okay, so none of these charges would go and float across the charge that I've stored previously across this output capacitor CH, right? So all of these capacitors that we're trying to move here is actually being absorbed by this M2 transistor to create its channel. Okay, so now in order to have such condition, I need to work out with the aspect ratios. Now if at all, if this oxide capacitance are same and the effective gate potentials are same, and even if I assume that the L1 is exactly equal to L2, then I would end up having that if the value of this W2 is equal to half the value of my W1, then the job is done. Okay, so now so this is how I can eliminate the channel charge injection error. Okay, so let us look into the actual circuit more clearly. So this is what I said, like this is the delta Q1, and I assume that this delta Q1 represents half the QCH value. Okay, and that is being utilized by this channel, and that's how none of these charges would float onto this capacitor to disturb the voltage across the whole capacitor. So let us look across the drawbacks of this. So now in this case, the assumption of equal splitting of the charge between the source and the drain is always in general is invalid. Okay, so we are not sure about what is the type of impedance that the source terminal sees and what is the impedance that the drain terminal sees from the M1 channel, right? So because of this, the assumption of this equal charge getting distributed through the drain and the source is generally invalid, and due to which the sizing of this M2 that I am trying to make as the width to be equal to half the size of my width of my M1 is generally becomes invalid. Okay, purely it doesn't work. Okay, so let us see whether it could eliminate the clock feed through error. So as I said before, the clock feed through happens to be due to the overlap capacitance that hangs between the source and the gate, as well as between the drain and the gate, right? So this is what I have, and the assumption of having this W2 equal to half the value of W1 is valid even here. Okay, so with that we will try to work out. So now whenever the clock makes a transition from high to low, what happens is this creates a negative voltage onto this V out, right? So this is what I stated before. Just because there is a negative transition, there is a delta V change that it induces onto this V out. So the V out is defined as V in minus delta V due to this negative edge. But whereas the other device is actually makes a positive transition. Okay, so now this positive transition flows through two overlap capacitance, and you could able to see that this total effective capacitance that I have between the gate of this M2 transistor to the V out node is actually twice that of W2 times that of COV. Now the question is, can this positive transition actually makes a positive delta V across our V out? It seems to be confusing, right? Just because we have a factor 2. Remember that the value of W2 is actually equal to half the value of W1. So the 2 from here and the 2 from here actually cancels, and in the place of W2 I can just substitute the value of W1. So the capacitance that I have here, is actually same, and due to which the value of this delta V that is induced by the M1 transistor is same as that of the delta V that is induced by the transistor M2. So they both have the same magnitude and they actually cancel each other, and due to which I can eliminate this clock feed through error by making use of the dummy switch. So as far as the dummy switch is concerned, it clearly indicates that I can eliminate the clock feed through error, but it doesn't eliminate the error that is induced by the channel charge injection. So now let us look for the second type of switch, which is termed as complementary switch. So as the name suggests, here we are going to use two type of transistors. One is a PMOS, the other one is an NMOS, right? So it is actually the TG transistor that we have discussed for the switch. Yeah. So now let us see whether this can eliminate the channel charge injection problem. Clearly, one can write, let me label these channels with appropriate transistor numbers. So let me label the top transistor to be M2 and the bottom transistor as M1, so that the delta Q1 represents the channel charge of my M1 transistor, which could be represented as something like the length, the width, COX times that of VGS. Okay, so where VG is connected to a positive potential in order to make this device on. Okay, so which I take it as VDD, minus the VS term, where the VS is assumed to be equal to V in the moment I'm trying to turn off the device. Okay, minus VTN, and this is the channel charge that I have across my NMOS channel. And similarly, one can write the channel charge across the M2 transistor as delta Q2, which is again would be equal to W into L into COX times that of V in times that of VTP. Okay, so clearly I need to have a term which is supposed to be equal to VSG, and we know in order to activate this PMOS I need to have a zero potential across the gate. So the VG is basically equal to 0, and what is connected to my VS is generally my V in term, and that's the reason why we have plugged in the value of V in the place of VSG. Okay, yeah. So now note that the delta Q1 is generally negative in charge, just because I need electrons to fill this particular channel, whereas the delta Q2 would be generally a positive quantity, just because I need holes to fill this particular channel, right? Now clearly, if these two quantities are equal to each other, the moment I make this device turn off, so what happens is these charges would generally tries to distribute towards these terminals, and they attract each other and they cancel each other at this junction itself, right? So generally these charges, when they are equal, then there is no issue with this channel charge injection. But this happens only when I have V in that is equal to VDD by 2. Remember that these quantities are not equal. Okay, and under the assumption that even if I assume that my VTN is exactly equal to my VTP, still only for a specific value of Vin I could make these two quantities to be equal, and in general I can make this delta Q1 exactly equal to delta Q2. So again, this particular method fails to cancel out all of the channel charges that are moving towards the whole capacitor. So as stated before, the cancellation occurs only for one specific value of the input. There is also one more thing that one has to encounter with respect to the cancellation of our clock feed through. Okay, yeah. So clearly the clock feed through error is not completely eliminated, just because in general the COV of NMOS is not equal to the COV value of our PMOS. Okay, so due to which in general they will not cancel each other. Okay, so that's again a drawback even from the perspective of the clock feed through error. Okay, so now let us move on to the third type of switch, which is termed as the differential switch. So now clearly there are two type of inputs, Vin1 and Vin2, and as the name suggests, I have two type of switches, and these switches are generally operated with the same type of signal, which is the clock, and both this device M1 and M2 are basically built by making use of this NMOS transistors. Now if that is the case, if all these things are identical, then we know that one could express the channel charge, which is delta Q1, to be equal to the same expression that I wrote it before. So except that this was represented as VDD, nevertheless it is equal to VCK here. Okay, so it's the same thing, like VCK or VDD or one are the same. Yeah, so clearly we could see that the channel charge that is stored under transistor M1 and the channel charge that is stored under the transistor M2 is being represented in this case. Now if I could able to read this Vout1 and Vout2 differentially, which means that if I am trying to read these two nodes differentially, then the error that caused due to the charge movement across the output capacitor would impact the same way that this delta Q2 would have impacted. Okay, so this error that is caused due to this charge injection onto my output capacitors seems to be a common mode error, and when I read the outputs differentially, then this common mode error in general could be eliminated. But this is only possible when my inputs are same, so that has to be clear. Okay, so these two terms would be equal to each other only when my Vin1 is exactly equal to Vin2. Okay, so what I really mean is, if at all, if my Vin1 and Vin2 represents the differential signal, then the delta Q1 will not be equal to my delta Q2. So whereas if my Vin1 is exactly equal to my Vin2, then this delta Q1 would be equal to delta Q2, and they impact the output capacitor CH in the same way. And then when I try to read the output voltages Vout1 and Vout2 differentially, then I could eliminate this channel charge injection error as a kind of common mode error. Okay, so there is something that works in this particular way. So again, this method seems to be not pretty much doing good for us to eliminate the channel charge injection. Okay, but it has certain advantage when we compare with the previous techniques like dummy switch as well as the complementary switch. Okay, so in general, since we are reading the errors differentially, it actually removes the constant offset error. And also one more thing is that it eliminates the nonlinear it doesn't eliminate, but it lowers the nonlinear component of the error. So I said before that this particular term has involvement of something like x by 2 and x square by 8 and then x cube by 16 and then a negative term, and after then a whole lot of things, right? So since because our Vin1 and Vin2 are appearing inside this square root, one could express in this particular expression. And now since because I'm trying to read them differentially, what happens is the terms that are even generally gets cancelled out. Okay, so that is what I'm trying to say here. It ends up having only the odd ordered distortion at the output. Okay, so there is a bit of advantage when we compare with the previous techniques that we have discussed. Okay, so now let us come back to the final type of method, which we call it as a bottom plate sampling. Okay, so as shown here, there are two type of switches when compared to the previous methods where we had only one type of switch, and we were trying to use this switch either with NMOS or with the TG transistors, right? So, but rather than having a single transistor or a single switch, we also have added one more switch here. Now the timing detail of these two switches are given here. So clearly it states that the phi 1A switch in general turns off much earlier than this particular switch. Okay, so what I really mean here is, like, let us assume that for time t that is equal to t1, what happens is this switch is actually closed, and just before this time t1 even this switch would be closed. So what happens is, right now it is the time in which I'm trying to sample my input onto this capacitor CH. So the moment I reach the value of t1, then this switch generally turns off. That is, the switch is open, and now what happens here is that this particular capacitance CH poses an infinite impedance rather than 1 by SCH. Okay, so this was the impedance for the time that was before t1. The moment turn off this particular switch, the impedance changes from this value to an infinite impedance, okay, at time t equals to t1. Now, due to which, what happens is, the moment I turn off this switch, the channel charge would tries to see an impedance which is not finite, but rather it is an infinite impedance. So what happens is, none of the charges will try to move towards this particular path. Just because of infinite impedance, all of the channel charges would try to move towards the other way and goes through the voltage source towards and discharges through the ground. Okay, and this particular technique is termed as bottom plate sampling. So the bottom plate sampling has two types of switches, out of which one of the switch turns off a bit earlier than the other switch. Okay, and the timing details are been given here. So this seems to be much more genuine way by which I can completely eliminate the channel charge injection problem. Okay, and the same thing is been reflected for a time that is less than t1. This capacitor CH poses an impedance value which is 1 by SCH, and later on at time t equals to t1, the switch opens up, and due to which the same path represents an infinite impedance, and the moment when the time t reaches the value of t2, this particular switch turns off, and these channel charges finds an infinite impedance to the path towards the Vout, and due to which now the channel charges moves towards the whole capacitor, and all of these capacitors would try to discharge through this particular path through the V-in source that we have connected. Okay, none of the charge moves towards the Vout. Yeah, so this is a practical way where this phi 1 switch as well as phi 1A switch is being replaced with appropriate transistors. Both are being built by making use of NMOS structures. So with this, I will complete this hold phase as well as the methods to remove the errors that are induced during the hold phase. So see you in the next part 3 session, where we will discuss about the applications of the switched capacitor circuit.